Good afternoon, everyone. Welcome to our beautiful UCSB campus. I hope you're enjoying your time here. I'm Tresa Pollock, as you heard, and today my lecture is going to focus very broadly on the topic of exploration. And I think we all dream of exploring, say, maybe the remote stretches of the US. I personally dream of visiting every national park. Perhaps you dream of going to New Zealand for the weekend, or maybe some of you would like to actually explore another planet. And so, what keeps us from doing that? Well, the major problem is the ability to get to these places quickly and in a safe manner. And so what limits us in doing that is often the propulsion. How do we get from here to there safely? And how do we improve that such that we get a chance to explore all of these places? Now, I will remind you that exploration is sort of with us from the earliest days of our lives. As soon as we acquire that first mode of propulsion, that would be crawling, we must explore what's behind that cabinet door and begin to build something. We have no idea what that is, but it's something we'd all like to be better at, propulsion and exploration. Now, we have a tendency to hold in very high regard our explorers. I probably do not have to tell you who any of these explorers are, because they're all very well known, and they have taken risks to do the things that they have done in aviation and in space. But what I would like to convince you of today is that that's just the last stage. There are many exciting things to explore in preparation for the moment when one undertakes one of these feats. And what we really need are more explorers who explore science, engineering, and design. And I hope today to show you some of those places that we would like you to spend more time exploring. Now, when John Glenn left the Earth and went into orbit, even though I'm a great fan of his, I'm from Ohio myself, I know that he was not responsible for the rocket engines that took him there. And so there's a whole host of interesting people and problems behind these sorts of efforts. It takes a lot of science, engineering, design to go into orbit, to break the sound barrier, and today I would like to share with you some of the things that leads up to these sorts of capabilities. Now let's go back to the beginning of aviation. As I already told you, I'm from Ohio, Dayton, Ohio, which is known as the home of aviation. And if you go back to the very beginning, there were two brothers, Wilbur and Orville, and they owned a bike shop, actually, and they were good engineers, but they didn't believe that bicycling was a fast enough mode of propulsion. So they decided to design and build an airplane. And I think we all know how this turned out. In the end, they were able to fly at Kitty Hawk. But what were the challenges they faced? And so there were two major things. They had to figure out lift, drag, and how that translated to the design of an airplane wing, which they did. And then the second, perhaps more challenging problem, is once they knew that, they decided that based on the lift and the drag calculations, they needed at least an 8-horsepower engine generating 90 pounds of thrust, and that engine must weigh less than 200 pounds to achieve a minimum airspeed of 23 miles per hour. Thank goodness planes go faster than that now. So what to do? At the same moment, the automotive industry was developing. Henry Ford was just up the street. There were people building engines for automobiles. And so the Wright brothers went around and talked to them and found no solutions. And why is that? Well, because all automotive engines were built from steel. And they knew that if they built this from steel, that it would be way heavier than 200 pounds. So there was this new company in Pittsburgh called the Pittsburgh Reduction Company, and they were making a brand new sort of material, aluminum, which is obviously no longer brand new, but they went and acquired some aluminum and basically set up a foundry to make castings of aluminum, and in the end, they were able to make this engine that was largely composed of aluminum and light enough to allow that Kitty Hawk flight to occur. So there are lots of interesting problems to be solved, and then there was the final flight, which of course is what got all the publicity. Now, if we think about propulsion in its current form, probably the two most advanced systems that bring us large amounts of propulsion are, one, aircraft engines. These are on the planes that we all fly around on every day, and then rockets. And both of these systems create massive amounts of thrust by combustion of fuel, and they have a lot of challenges. You can see from looking at these movies on the left, we're just testing an engine in preparation for qualifying it for service. We have an actual launch of a rocket on the right. And these are obviously, just from inspection, very severe environments. Okay, the Saturn V rocket, I want to talk a little bit about both because they are different. Rockets are often fueled by a combination of liquid hydrogen and liquid oxygen. And so this is the rocket that took the astronauts to the moon. And this is a close-up of the nozzle that's producing all of this lift. And just to give you some sense of the environment, in here we have pressures of about 3,000 psi and temperatures over 3,000 degrees C. Now this nozzle is mostly composed of copper and nickel alloys, which melt at 1084 and 1452 degrees C, respectively. If you fast forward a little bit from the Saturn rockets and the Apollo environment to the Space Shuttle main engine and more modern rockets that take off at Vandenberg, it seems like almost daily, there are different challenges as they become more advanced. And here's an example of another challenge. This is the oxygen pump that is just above the nozzle in the main engine. And you can see that after a test, this nozzle is completely gone. It has burned in the high-pressure oxygen environment. And so it was a major challenge to find materials that would survive in those sorts of environments to make these more advanced rockets possible. Now let's turn to the gas turbine engine. These are composed of basically 4 sections. We have a fan, we have a compressor, we have combustion, and then we have a turbine. And so up here we compress air through the fan and the compressor. That high pressure air goes into the combustor with fuel, and then we have very high pressure, high temperature gases coming into the most critical part of the engine, the high pressure turbine. In that section of the engine, the hot gases that are at about 1500 C. And if you're flying, say, in a salt environment, you may have residues of various sorts that come along with that hot gas. Now, looking at the materials of construction from the front toward the back, we start with composites or maybe aluminum alloys in the fan. This has to resist bird strikes. That's one of the critical tests for an aircraft engine. You throw a frozen chicken in the front and that fan blade cannot break. Then we go on back and we have titanium alloys, mostly in the compressor. Then we combust, and then almost everything behind that is composed of nickel alloys. And the progression here is basically they have increasing melting temperatures. And so you get hotter and hotter as you go toward this high pressure turbine. Now, as you all know, with regard to flight, commercial flight, safety is obviously the main concern. And flying is incredibly safe. I don't want anyone to think it is, but it needs to be so safe that we have to understand the materials in incredible detail and make sure that when and if they do fail, that we know everything about how it happened. And so here is my favorite failure. I know that seems a little weird, but it's my favorite failure because of, one, nobody got hurt, and two, of the way it unfolded. And so this was an American Airlines Boeing 767 that was coming into Los Angeles in 2006. And the pilots noticed as they were approaching the runway some very strange vibrations. They were so close to landing, they went ahead and did that. They unloaded the plane, and everyone went off to get their bags, and they rolled the plane around to the part of the airport that's remote, and they powered up the engines to full throttle, and one of the high-pressure turbine discs failed. And so you can see half of that disc right here, and you might have thought that that disc came out of this engine, but no, it came out of the engine on the other side of the plane, bounced under the plane, up and destroyed the second engine. So that's pretty amazing. Now, the question, of course, is how could this happen? If this thing fails, that's literally the most dangerous failure you can have in an engine. And so there are detailed investigations, but the bottom line is typically in these situations, there may or may not be some tiny defect, but we develop a crack, and then every time you take off and land, that crack grows a little bit. And eventually it grows long enough to cause that thing to come apart into two pieces. And so what we always want to understand in more detail, and it's what's challenged the development of materials, is understanding in great detail what are the defects and how do they lead to failure. Now, before I tell you more about that, I have to say a little bit more about what the structure of most materials is like internally, if you look at them in the microscope. So most solids, things like metals, ceramics, so forth, are composed of billions of tiny little crystals. And so I show here a collection of little crystals. And within each one of those little crystals, the atoms are stacked up pretty perfectly. And then each of these crystals will have a different orientation. So where they come together, the structure is less than perfect. And so those regions are called grain boundaries. And they are often the source of initiation of defects. And so here's an example of a turbine blade. So that would slide into that disc and rotate to generate thrust. And this failure has basically occurred by damage that develops in between these little grains that eventually joins together and causes this failure. And so, as engineers, what might you do about that? Well, this was an interesting question. Some years back, there was an engineer at GE that said, well, if the materials are failing at the boundaries, why don't we just take them all out? Let's make them single crystals, just one crystal for the whole blade. And so there was a lot of effort that went into that, and it's a little bit hard to see here, I think, but this blade is polycrystal, billions of grains. This one only has grains running up and down because it's the ones that are transverse to the axis that accumulate the damage. And this one is a full single crystal. And now about 95% of the blades produced for aircraft engines are indeed single crystals. Now, it's not easy to do this. This is one of the things that we do research on, and I have for many years. This gives you an overview of how you would grow a single crystal. So you start with an ingot material. There's a furnace here that you can't see very well that will be preheated to about 1575 C. Inside that furnace will be a ceramic mold, so you melt and pour material into that. And then what one has to do is withdraw from this hot furnace into the cold zone, i.e. you develop a thermal gradient right here. So all the action's right at this interface. And you can see the temperatures changing very rapidly just from the color here. This is a little bit accelerated. You have to do this very slowly at 8 inches per hour. And so here we're not growing blades because we're trying to do research and make test specimens. But you can see some of the tricks are in the beginning. You get a bunch of polycrystals down here, and then you force them to grow in ways such that you only have one emerging at the top. And so there's lots of details about controlling the thermal conditions here to arrive at this series of events. Now, one of the things that I was instructed to do very early in my career when I worked at GE Aviation was to find a better single crystal alloy. And so very quickly I found an alloy that had a lot of strength. Great. And then they said, okay, Tresa, make some blades. And you don't have to be an expert to look at this blade and realize that's not a single crystal, right? There's these grains here and down here. And so the mystery was, well, why does this happen? And so it took actually many years and lots of very complicated characterization in 3D, not 2D, and calculations to sort out the fact that these are started by what we call convective instability. So you develop density gradients in the liquid, and that kicks off these little currents, and those little currents create grains. And so we figured out how to balance the chemistry to avoid that, and in the end, this blade could be made as a single crystal. Okay, so there's lots of places along the way you can introduce defects and have failure. Why is it so hard? And so there's sort of two sets of reasons why it's so hard to avoid failure. There's the application environment, as we've talked about, high temperatures, the stresses, particularly cyclic stresses. We have corrosion, we have oxidation, we have joints, we have coatings, and then sometimes people don't listen, and they use the aircraft, for example, outside the design envelope. They push it too hard, and then a failure happens. But there are also unanticipated things about the environment, and I show an example here. And this is one of those things that you never would have thought about when you were designing the material, which is, this is a photo of the volcano whose name nobody can pronounce, that exploded in Iceland in 2010. And so you can see volcanic ash coming up through the cloud layer here. And this picture was taken by a Delta Airlines pilot, a friend of mine, Peter Green. He assures me that it was a really good lens and he's not as close to this volcano as it looks. I don't know if that's true or not, but shortly after he took this photo, this whole stretch of the sky was shut down, because if you ingest volcanic ash into your aircraft engine, it will melt and infiltrate things and cause failures. So an example of an unanticipated failure. Now on the material side, the questions are, do we have suitable materials? Can we manufacture them into the appropriate forms? Do they have the properties that we need after we manufacture them? Or do they contain defects? And then how would they respond to an environment that you can only imagine? Now earlier I talked about the need for high temperatures. And so I show a chart here that has the melting temperatures for all materials that can operate in excess of 1,000 degrees C. Recall I said earlier that a lot of times we're using nickel alloys, and strangely enough, they're at the low end here. And there's all these other materials that have higher melting points, and yet we don't use most of them. So why might that be? Well, there are two reasons. Probably 2/3 of these are incredibly brittle, so you can't make anything out of them. And then the others oxidize incredibly quickly so that they wouldn't survive in these environments. And so the other thing related to that, or I guess this is a reflection of that, is to use a material in a severe environment, you don't just need one property. You don't just need a high melting point. You need a whole suite of properties for the engineered object to survive. And even worse than that, Some of these properties, like melting, that's kind of related to the atomic structure, pretty reproducible. But other things like fatigue that cause that turbine disk failure rely a lot on aspects of structure that exist over cubic millimeters. And so now we need tons of information down to the atomic level over cubic millimeters of material. And that's very expensive from the point of view of characterization. Now, so I said we have all these length scales. I want to show you a video here of a turbine blade made by a colleague of mine, Günter Egler. And you'll notice there's a scale bar at the bottom. This is 500 micrometers, 10 to the minus 6 meters. There's a defect. What this basically is a montage that fades in and out of images taken from 5 different microscopes. And so here we're down to the 2-micron scale, and you can see all these blocks. And these are actually a different crystal structure than the material around them. This is what we'd refer to as a 2-phase material. And these blocks of material are what allow the nickel alloys to be so strong and operate up to 85% of their melting temperature. Now, earlier I said we need alloys, and what we really are doing is mixing together a lot of elements, but we have to figure out which of the phases the elements go to. And so everything shown brightly here sits in the blocks, which we would call precipitates. And then the cobalt, chrome, rhenium, all of those things sit in the mortar, if you will, that hold the blocks together. And so the point is we have a lot of length scales. We have to worry about chemistry. We have to worry about structure. And so here now we refer to things in the micrometer scale as microstructure. Now we're going to go down to the nanometer scale and on to the atomic scale. And so we have a lot of different expensive microscopes to do this, but it takes a tremendous amount of time to get all this structural and chemical information. And so you're going to see here that eventually now we're getting down to imaging at the atomic scale. And so these are cubic atomic structures, and you can see that there. Now, earlier I talked about the need for things in 3D and the fact that we need structure and chemistry. And so this has led my research group to build a brand new kind of microscope. And we refer to this affectionately as the tri-beam system. It doesn't take too long to figure that out. It's because it has an ion beam, an electron beam, and a femtosecond laser beam. And then all this other stuff are detectors to detect structure and chemistry. Now, the role of the femtosecond laser is to serve as basically a nanometer scale knife. It will ablate a layer of material without doing damage and then allow us to get structural information. And so you can see the layers being removed in this movie. This is an additively manufactured alloy that usually we expect most additively manufactured alloys to have a lot of defects, and indeed this one does. And you can see them as we slice through the material. And so this is sort of gives you some idea how long it takes. People used to do this mechanically, so we can do a slice in 25 seconds. That used to take hours. So this is very, very fast by standards of things that came up to this. And now there's a commercial version, which is much prettier than the one I showed you. It's sitting in boxes in Elix Hall, waiting to be put together. Okay, so the femtosecond laser, I don't have time to tell you a lot about this. I got the idea to do this at the University of Michigan. I used to share the hallway with Gerard Moreau, who recently received a Nobel Prize for his work on lasers. And that collaborative work is what started this idea. So always talk to the people in the hallway, that's important. Now, this is kind of a library of all the different things we've been able to make 3D data sets for. And the point here is that if you can section geological materials and ceramics and metals and mouse brains, then you have a generically useful instrument that a lot of people will be interested in. So here, back to our turbine disk material, this is what the structure looks like. And I just want to tell a very quick story about what we've learned from having that 3D data about this material as it relates to that fatigue failure. And so you can see in this structure, there's all these red-blue contrast, and it turns out all these red-blue kinds of boundaries are very special low-angle boundaries. They're all imaged in blue here, and they have sort of a very special mechanical effect on the material. The thing that was surprising to us was their distribution and how they were interconnected in a way that nobody had realized before. This gives us a story about how defects develop and propagate. Now, what do I mean by defects? Well, this is kind of a long story. You're going to have to come here and take a whole class from me. But defects, when you bend a bar, there's lots of these defects called dislocations that will move through. If they get near a surface, they exit the surface, and they leave a little step like this. And so we've developed a technique to look at all the different defects coming out of the surface and what is the amplitude of the displacements that are caused at the surface. Now, why might that matter? Well, I'll explain that. So this is actually an image showing two things superimposed, one cycle in tension, one cycle in compression. So if you go tension 0, compression 0, you should be back to where you started. But in fact, some of these defects, because they exit the surface or get stuck, in fact, don't go back to where they were. And so these special regions that persist and are irreversible basically are the source of these little tiny cracks that start and that have nothing to do with extrinsic defects. It's just a part of the material itself. And so a big mystery solved in this case. Now, the other thing that the 3D data allows us to do is look at all these crazy, complicated clusters of grains and how they act together to allow that crack to continue to propagate, and to get statistical information about who's the most intense one and which is the configuration that will give us a crack. And so there's lots of other things you can do. In this particular case, what we're trying to do is say, all right, if we know we can predict the crack starts, for example, here, how will it propagate through the material, and how will that result in a big macroscopic crack? So there's lots of questions that can be answered if you have this level of fidelity of 3D data, and artificial intelligence and machine learning techniques are giving us a new opportunity to use that effectively. Now, another thing that we've done to understand this, we're very impatient people, so this fatigue process, every landing cycle, we've found a way to speed this up by testing at 20 kilohertz. And so now what used to take us months or years to get the information we can do in days. And so connecting this kind of fatigue macroscopic information to this very local information, what we've discovered is we can just get this very local information in one cycle and predict when a material will fail, at what strength or what cyclic stress the material will fail in 1 billion cycles from now. And so very exciting times from the point of view of being able to predict what will happen next. And so my very final point, we have all of this 3D capability now at the same moment when 3D printing is becoming a very, very important thing for propulsion, both aircraft engines and rockets. And so I think you all know how 3D printing works. You drag some powder across, you take the laser, and in the pre-programmed part, you make it dense. And again, by making those 3D data sets, we can understand how to change the parameters of these systems and achieve the structure that we want, and to achieve new designs of alloys that can actually be printed without cracking. And so that is the topic of much of our current research, both on the aircraft engine side as well as on the rocket side. So I hope that I've conveyed, there's a lot of places you can explore. Some of them are at the nanometer and micro scale, and that there are many, many interesting challenges standing in front of us. And I would like to end by thanking my own explorers. This is my research group who did many of the things that you just saw on this slide. So thank you very much, and I think I'll have a chance to answer some questions for you.